Great. Hello, everybody. My name is Dong Ping, and I'm a fifth-year PhD student in camp. So today it's my pleasure to introduce Professor Lexing Ying, our camp colloquium speaker today. So he's a professor of mathematics at the Institute of Computational and Mathematical Engineering at Stanford University, which I'm pretty sure lots of our camp field faculties are quite familiar with. Prior to that, he was a professor at the University of Texas at Austin. He received his PhD from Courant Institute at NYU and was a postdoc scholar at Caltech. So as a numerical analyst, I actually know Lexing's work for a long time, but I never get a chance to speak with him. So during the pandemic, one day I was listening to one of his talk and thinking, why not ask him to give a colloquium talk here. So as you all know, every year students in CAM get a chance to nominate whom we want to invite to give a talk here. So this year I nominated him. We voted him as our student selected speaker, and he kindly accepted my invitation. So thank you again. And by the way, I'm actually in the room of where we usually hold our colloquium, just to give you a feeling of what it usually looks like. Okay. So for those of you who probably already know, Professor Ying is known for his work in numerical analysis and scientific computing. Some of his work include fast and accurate algorithms for oscillatory integral transforms, high frequency waves for electron structures, to name a few. But if you visit his website, you'll actually find lots of other topics which don't fall into these categories. So I think clearly he already expanded his interests. He received lots of awards, including the Sloan Research Fellowship, the NSF Career Award, the Feng Kang Prize of Scientific Computing, the James H. Wilkinson Prize in Numerical Analysis and Scientific Computing from SciAm, and the Silver Morningside Medal in Applied Mathematics. And today he's going to talk about the Sobolev regularization of stochastic gradient descent for neural networks. Before letting start, just a few words about the logistics of our colloquium. So it is being recorded, so if you don't mind, please keep your microphone muted, but feel free to leave your video on so that we can have a second order approximation to an in-person colloquium. To ask a question, you can either use the hand raise function in Zoom, or you can put it in the chat window. I'll keep an eye to it, and whenever there's an appropriate pause, I'll let you unmute yourself and ask your question. And Lexing said he's comfortable with being interrupted during the talk. Okay, I think with all of that, Lexing, please, the floor is yours.
Yeah. Okay, great. Thanks, Tongping, for the nice introduction. So I'd like to thank the students and also the camp organizers, colloquium organizers for the invitation, and it's especially a privilege to be selected by the students as a speaker, and especially once per year. So thank you very much, and I really appreciate that. And I also had the chance to talk with faculties at a camp and the students at camp this morning, and learned a lot about Cornell and your camp program. So very exciting. So okay, so today I'm going to talk about some recent work that I did with Chao Ma, who's also at Stanford, on this topic, which is called the Sobolev regularization of stochastic gradient descent for neural network. Okay, so I grew up as a numerical analyst, and so most of my work is in numerical analysis and applied PDEs, and I only started working on machine learning stuff a few years ago, and but I find the topic to be fairly exciting, and in fact, a lot of things that we learn in numerical analysis actually can play a role in explaining some of the key problems in machine learning. Okay, let's get started. So let's dive right in. So the topic I'm going to talk about in today's talk, two things, right? Neural network and SGD. So I always use NN to stand for neural network, and SGD to stand for the stochastic gradient descent. Okay, so here we are going to be quite flexible in terms of the structure of the neural network. So, but to be specific, we're going to work with multilinear neural network, and so multilinear neural network is the following: is that it's essentially representing a function called fxw, where x is our input and the W is the collection of all the possible weights. So a feed-forward multi-layer neural network does follow, right? So you take an input and you multiply within a matrix, it's going to give you another vector. You apply some activation function to it, it gives you another vector. You apply the second layer of the matrix, and you keep doing until you go to the last layer and you spit out the answer. So this is a very simple form of a multi-layer neural network. Now, typically these neural networks are trained with various kind of training algorithms, and the most popular one is called Stochastic Gradient Descent, the SGD. And there are many other algorithms involved, like Adams and MS-prop. But in this talk, we're going to stick to the simplest one, which is a SGD, Stochastic Gradient Descent. Now, if you ask the people working the theory of neural network and machine learning in general, and what is the most important question for a neural network? And I guess at least 50% of them will say that the key question is that why does SGD generalize? To be more specifically, what this means is that suppose SGD find a solution, which is W, and why does this W, the neural network given by this W, give you a good result when you try it on the testing data? Right? So this is called generalization. Now this is also and people also refer to this as the implicit regularization of the stochastic gradient descent. Okay. Now, if you take a look at the literature, and the typical explanation, a little bit hand-wavy explanation, is that, well, people say, aha, this is obvious. Why? Well, because SGD prefers to find the flat minimum, okay, and then the flat minimum obviously generalize well, okay. But if you take a look close at this explanation, I mean, a lot of things are not clear. So, what do we mean by flat minimum, right? So here the neural network actually depends on the two things. One is your input X, and the other neural network weights W. So when you talk about the neural network optimization SGD, find the flat minimum, well, that actually refers to flat respect to the W variable, okay? Because this is what you optimize. Now, but the good generalization is not about W, because you have to try it on the new data sets. So therefore, the generalization property is actually on X. So in fact, this explanation is actually the only thing it does is to turn into two problems. So why does SGD find a flat minimum? And second is why flat minimum generalize better. So in this talk, what we're trying to do is that we're trying to turn this explanation into somewhat more precise mathematical statements. Okay, so the statement will show the following: is that first is that SGD will find a solution such that the gradient of your function respect to the W, my neural network weights, is small. Okay. And the second is that we can also show that once you find the gradient respect to W is small, and the gradient respect to X is likely to be small as well. Okay. Now, so this poses two questions for us. First, why this is true? Why the first step is true? This is question one. Why SGD makes the gradient of the W, a gradient WF XW star small, and here X star stands for the true solution, the solution the SGD found. And the second question, the second step is that why does the gradient in W small imply that gradient in X is small as well? Okay. Now, I will just review you the solution. What is our answer? Okay. The answer to the first question, I will explain, I mean, the rest of the talk will try to explain these answers and try to prove it for you. The answer to the first question here is that the stability of the SGD imply the flatness. Flatness meaning that the gradient with respect to W is small. So stability, I will make it more precise. What do I mean by stability when I get to this part? But the stability essentially saying that if SGD finds a solution W star, it tends to linger around in W star with very high probability. It is not very likely to escape. So in fact, because SGD is a stochastic algorithm, when you say that it finds a solution W star, this is probably what you mean. It's going to wander around a certain solution W star, doesn't live around it, right? So for people who work in stochastic calculus, you know that if you do a stochastic gradient descent or any kind of stochastic differential equations, you will not stay at the one point forever, right? You're going to wander around at your global minimum for a long time. Now, the answer to the second question, why the gradient W small imply the gradient of X is small? So here, we're going to use two things. And in fact, the most important thing is actually come from the neural network itself, is a so-called multiplicative structure of the neural network. Okay, the multiplicative structure plus the flatness will imply that the gradient, the bound on gradient W can be transferred into gradient X. So this is the very dense slides, but I just want to put it out here. What is our main argument? I mean, what is our main explanation of the SGD generalize? Okay. Now the talk will naturally become into two parts. And the part one is going to try to explain the first question, answer the first question, and part two will answer the second question. So when we wrote the paper, you see that we answer the first question first and then answer the second question. But actually, like many people, when you're experiencing doing research, often you do backwards, right? You're trying to, I mean, this is also what happened to us. So we find a solution for the second part, and we identify the flatness as a key concept to link this the whole pipeline together, and then we prove the first part. So in this talk, I will just take you along that journey, and let's address the second part first, and then go back to the first part. So by second part, I want to understand why the gradient in W small can imply gradient in X is also small. Okay. So as I said, let's start with the second part. Why flat minimum generalize better? I.e., why can we transfer the gradient in W to gradient in X? Okay. So as Dongping pointed out, I also want to return it again. So if you have any questions, please stop me. And in fact, the things what I'm going to explain is quite intuitive, but also it can be quite a little bit technical because it's a theory result. So if anything is not clear, please do interrupt me. Okay. So what do I mean by the multiplicative structure? Well, the multiplicative structure is very simple. It's just this architecture of the neural network. Is that every step you get a new result, you can multiply a matrix on top of it, and then you go to the next step and so on and so forth. So in fact, as you will see that I only need a multiplicative structure for the first level, is that whenever you give me an X, I'm going to multiply with neural network weights W1 and then feed it to the next layers. Now, it's useful to introduce some kind of some actual notations. So we're going to use HI to stand for the result you get after you apply the ith neural network layer. So for example, after the first activation, I call it H1. After the second activation, I call it H2, and so on and so forth. And using that, it's a little bit easier to write down the whole formula. Now, when we calculate the derivative of the certain neural network, we use this famous chain rule, right? This is called backpropagation. So if you write down the derivative of my neural network with respect to W1, let me remind you, W1 is the weights at the first layer. This is the formula that we get. You take the result of the neural network, take the derivative with respect to the last layer, and the last layer respect to the layer before that, and so on and so forth. And this first layer is going to take the derivative with respect to W1x, and finally, W1x is going to take the derivative with respect to W1, so you get an X vector here. So this is how you get the explicit formula. This line is written down complete calculation of the derivative with respect to the weights of the first layer. Now, we can also do the same thing, is trying to calculate the derivative of the neural net with respect to the input X. And you see that because of this layered structure, most part of the calculation is exactly the same, except at the last layer, instead of taking the weights taking the derivative with respect to W1, now I take the derivative with respect to X, so I get this W1 transpose here. What I want to highlight is that these two red parts are exactly the same. And this is a hint that we can somehow link the derivative of W1 with respect to the derivative with respect to X. Okay. To make it more clear, let's take a look at what is the norm of this gradient. Here I'm using two norms. Okay. So what is the norm of the gradient with respect to X? Now, using this formula, we know that the norm of this is bounded by the product or norm of these two pieces, right? This piece is here, and this piece is here. Now, on the other hand, what I can do is that I can try to divide a norm of X and multiply by norm of X. So I haven't done anything, right? This is just simple algebraic manipulation. This is the equality here. Now, if you take a look at the final piece, what is this object? So recall that if you take a look at this formula, so this is actually a vector. So this is another vector. So therefore, what you get here is the outer product of the two vectors. Now, because this is outer product structure, the true norm of this matrix, in fact, it's called a Frobenius norm of this matrix, is the same as the product of the norm of the two vectors. So therefore, this piece here is in fact equal to the norm of this piece divided by that piece. Okay? So therefore, the norm of this piece multiplied by that is equal to this. So this is what I'm using here. The product of these two things is in fact equal to the gradient with respect to W1. So you see that I have successfully linked the gradient with respect to X to the gradient of W1. Now, what is the catch here? The catch is that I have to pay a price. The price is the norm of the W1, Fubini's norm of the W1, divided. Here, I'm thinking about the W as a long vector. So therefore, the two norm here is actually the Fubini's norm of the matrix. But in the rest of the talk, I will always treat all these W's as the long vectors. So therefore, this is the two norm of this W1 weight vector divided by the norm of X. So therefore, as long as the W1 weights are not very large and the norm of X are not very small, right? Meaning that my input, for example, data, my X is somehow living on a unit sphere or somehow normalized. And also after the training, if my W1 is not too large, then I will be able to transfer any bound on W1 to the bound on X. Okay, so this is the key. Now, let's make it everything a little bit more precise so that we can write down a theorem. So as we said, the model we're going to have is just a feed-forward neural network with this multiplicative structure. So as you see from the previous slide, so far, everything important is only about the W1. I didn't care too much about the rest of the neural network. So in fact, all the theorem I'm going to state in this talk will work with any neural network as long as the first layer has this multiplicative structure. Okay. So therefore, because of this, I'll be able to write down conveniently as my neural network as the product of the first layer weight with my input, and then apply the rest of the layers. Okay, I denote it by F tilde. Now, the loss function we're going to work with is this typically L2 loss. Okay, we can generalize this to the some more general loss, but for the sake of the explanation and for the presentation, the easiest one to work with is this the quadratic loss. Now, the data is denoted by xi and yi, as I said, and the x is d-dimensional. D could be very large, high-dimensional problems, and w is I group all the way numerical of the weights of my neural network into this very long vector belong to Rw. Okay, so W is typically large. You can think about to be like hundreds of thousands of millions. Now we're working a regime, which I want to emphasize, I want to highlight here, is that interpolation regime. So this is a regime that become very popular, and it has been verified a lot in the experiments, is that when you have a lot of weights, you have a lot of representation power in neural network, the solution you typically find will interpolate all the training data, right? So here we assume, and in fact, this has been seen again and again in the neural network experiments, is that the W star you find is actually interpolating solution. The loss is equal to 0. Now, here's a key concept that we're going to use is something called a flatness. And this is a key concept which is going to link this answer of the question 1 question together. And it's called a flatness. And what flatness essentially tells you that suppose my SGD go to a certain set of weights W, right? I want to see that how curved, the landscape at that point. So this is essentially what the way you model this is that you take the Hessian of your loss landscape respect to the neural network weights, and then you take the trace. So this is essentially the sum of the eigenvalues of your Hessian, right? When the sum of these eigenvalues are large, this means that the landscape is pretty curved, right? The flatness is actually large. On the other hand, if this is small, this means that it's pretty flat there, okay? So flatness essentially is the sum of all the eigenvalues of the Hessian. Why this flatness is actually gonna link with my W1 weight that I talked about in the previous slides. The reason is it's a very simple calculation. You just expand what does the Hessian mean for this quadratic loss. So if you expand it, you just do a simple calculus, you see that this is equal to the sum of these two pieces. The first piece is the gradient times the gradient, and the second piece is the function value of f minus y times the Hessian of f. Now, Hessian of f will actually typically cause a problem because I didn't know anything about the later layers of my neural network. So therefore, in principle, this could be bad. But in the interpolation problem, this first piece is 0 because I interpolate my solution. The loss is 0. So therefore, at every point xi, this thing here is actually exactly equal to 0. So therefore, I don't need to worry about that. This piece is gone. So at the interpolating solution, this is a very strong assumption, but this assumption is verified in many numerical experiments of the neural network. Under this case, my flatness is essentially equal to the sum of the gradient of my W's. Okay. Now we're in good shape, because from the previous slide, I showed you what? I showed you that the gradient of x is bounded by this W1 weights divided by x, W1 2 norm divided by x2 norm, right? This ratio I was talking about earlier, times the derivative respect to W's. But now, because W1 is only part of all my W's, right? All W's are all the neural network weights. So therefore, this piece is bounded by the flatness, because the flatness is including all the weights. Okay. So therefore, flatness is, I mean, it's actually a very soft upper bound, because it's including all the weights at the later layers. But this is something that we decide to work with, and it's turned out to work for us. And so essentially, the main message here is that if you want to show that the gradient of my neural network respect to the input, the gradient respect to the input is bounded, all we need to do is need two things. The first is that we need the neural network weights at the W star is flat, meaning that this quantity is not too big. And the second is that the first layer weights is not too large, and also the input is not too small. Now, first layer weights is not too large. There's some theoretical analysis about this, but to be rigorous, I have to say this is, you can only check after you finish the training. Sorry, I have one mistake. This should be star here. Okay. Now, and the second is that the bound lower part, the x norm not to be too small. This I have fully control, because all I need to do is just normalize my image, for example, to make sure that all the image have norm 1. So then that's automatically fulfilled. Okay. All right. So let's now put this into a theorem. What the theorem says is the following. Suppose I have this layered structure in my, all I need is in the first layer. And suppose I denote all my data points, the training data at x1 all the way to xn. And then at an interpolating solution W star of my neural network weights, and this following statement is true. The derivative being x is bounded by the derivative being w, and up to this multiplicative factor. Okay. Now, here is a good point to explain why do we call this Sobolev regularization. Well, the reason why we refer to Sobolev is simply because we are taking care of, we're studying the derivative of this neural network, right? I mean, Sobolev norm, and it's essentially a norm on the derivative, and so therefore we refer to that as a Sobolev regularization. Now, yeah, okay. Now, one thing we need to do is that, in fact, and here I only showed you the 2 norm, but all the analysis that I have talked about can be extended to be any KP norm, right? So the vector P norm is that you take each of the entry raised to the power P and you sum them together and then take the Pth root. Okay, all the thing I have done can be extended to the P norm. So in fact, if you write, in fact, you'll be useful for the remaining of the analysis to use P equal to 2K. So think about the K to be a large integer, let's say 10. So then P is equal to 20. So therefore, we have a similar statement for the 20th norm of this huge vector. All the analysis remain the same, but the only difference is that the constant in front of it will be somewhat different. Okay. Okay. Now let me just first give you, so it's quite a lot of math, but before we do more math, it's useful to see some numerical examples and see some intuitions. Now numerically, let's give you some numerical justification first. So here I introduced 2 quantities, gx, gw. Well, these are the quantity we have already seen. This is the averaged x derivative, and this is the average w derivative of my neural network in the 2 norm. The reason why I want to write GWGX is because, I mean, for these labels, it become much easier. Otherwise, I have to write long formulas. So what I want to say is that I want to say that this GW actually serves as upper bound for GX, right? I want to show that this is actually happening in the real neural network. Now, I did 2 examples. We did 2 examples. So the first example is a fully connected neural network trained on Fashionist data set. So this is on the left-hand side. In this example, what we do is that we train the neural network with different learning rate. Okay, so in SGD, you can tune different learning rate and tune different batch size. Here we fix a batch size, which is around 20, and tune the different learning rate. And you see that this is the relationship between GW and GX. You see, it does almost look like a perfect linear relationship. So therefore, at least numerically, we show that it's safe to bound GX with GW. On the right-hand side, we have a numerical example obtained by training this VGG neural network on the CFAR10 dataset. And here on the right-hand side, the different dots, different color shows what kind of batch size we use. We use a batch size going from 10 all the way to 50. And again, you see that this curve itself is almost like a straight line. And in fact, it's actually bent down a little bit. But that's good because this shows you that we can safely bound the GX with a constant multiple of GW. So again, GW serves as an upper bound for GX. Okay, so the X derivative is bounded by the W derivative. So that's our numerical, these are numerical results on the real data set. Okay, for two different kind of neural network. So hopefully this shows you that our results is quite general. Now, here comes the intuition. Maybe I should put this slide at the beginning, but this anyway, this explains what's actually going on. You recall my neural network, it looked like the following. If X, W1, W2, But let's consider the simple case. Let's consider my neural network only has one single leg, is W1. And we know that in the neural network, in fact, is X multiplied by W1, right? It has this multiplicative structure. To make things more simple so that I can draw a picture, let's consider just a 1D case. That's X is just R1 and W1 is also R1. Okay, now I can draw pictures. The key is that because of this multiplicative structure, and in fact, the solution and the result of the neural network, what neural network produce, only depend on the product of X and W, right? So therefore, if on the left-hand side, you draw this picture in the W coordinate and X coordinate, and you see that this function F that I produce using this neural network architecture has to be the same function value along these level sets, because it only depends on the product of X times W, right? It will be the same value along these level sets. Now, what we're trying to do is essentially we're trying to transfer the smoothness of this function in the W space to the smoothness in the X space. Now, so what did the theorem say? The theorem says that I don't want the W to be too large or X to be too small. So if W is large, X is small, in this case, this bound is not very useful, right? I want the W to be reasonable, X to be large, so therefore I can get a useful bound. So in this figure, this will correspond to W not too large, so this will correspond to W here, X not too small, so corresponding to X here, okay? So I claim that on the left-hand side, in this regime, in fact, I can do this transformation. I can do this transfer because if W is not too large and X is not too small, what happens is that if you take a look at the landscape of this function, so it's more rough in the W direction and it's smoother in the X direction, right? So as long as you can say that on the W direction, I'm not so rough, then in the X direction, it can only be much smoother. The bad thing can only happen when the W is large. Let's say this regime, W large and X is small. If the W is large, it's possible for your function to be very smooth in W, but because of the squeezing of these level sets, it's possible for my function to be very rough in X. So therefore, the theorem that I proved is not very useful. But as long as I stay in this good regime to the left-hand side of this line, my theorem is useful, okay? So this is the intuition. I think this is probably the most important slides of the whole talk. So I would like to, for people who are interested, I think I want to get the message through. So, if you have any questions, I'll be happy to take them now. Okay. Okay. All right. So I hope everything is okay. Now, again, come back to the technical things, but let me just explain. So far, we have only proved that these norms, let me just take a look more look at this formal theorem we proved. So we proved that the gradient at X is going to be small at my training data set. Okay, at the training data set, I have good gradient bound. But in fact, that's not enough. In order to do generalization, you need to be a little bit, we want to say something about the points which close to my training data point. So therefore, to do that, this is what I'm trying to say here. We're trying to extend the result from the training data to a neighborhood of xi's, to a neighborhood of my training data. To do that, we need to introduce one definition, and this is the technical definition which we have to introduce. This is called something called C delta K local smoothness condition. I mean, once you look at this name and you know that it's a technical condition, okay, and we have to use in order to prove theorems. But what I want to say that this condition is very weak. What it essentially says is the following: is that I want to say that if you take a look at two nearby neural network set of weights, one is called W and one is called W prime. I want to say that if the weights doesn't change too much, then the gradient of my neural network is actually doesn't change too much either. In fact, this is not even a Lipschitz condition. It's much, much weaker. It says that suppose you know the gradient of my neural network, the W is this quantity here. Then if you move a little bit, the gradient cannot change by a huge factor. It's bounded by constant factor times the value over there, okay? So which means that if I know at a certain point, my neural network, my gradient in W is bounded by 1,000,000, and then, or maybe by 10, then I move a little bit, I cannot be bigger than C times 10, okay? But C could be some constant. For example, 100, then it cannot be changed by, suddenly jump to 1,000. Okay, so this is the condition on the neural network architecture. And I mean, for certain architectures, you can go through the analysis and try to verify that. But this is the condition we're going to use. Hopefully I convey the message that this is a very weak condition. It's much weaker than Lipschitz. Okay, it's now once we have this condition, we can extend our results at the training point for the gradient of the x to off training point. So to do that, we introduce this x delta. This is a set this is a small set of around this training data point. So what you can think about is that these points x1, x2, x3, these are my training data points. So for each of the training data points, I'm going to draw a circle around it with radius delta. And now I take the union, and this will be my set x delta. Okay. So allow yourself to move a little bit away from your training data. Now, what this result shows that the same bound that we had, the same result we had earlier, which meaning that the bounding the x derivative by the w derivative is only true to the training data, but also true in a neighborhood of the training data. Okay, so you will see why this is useful later. Okay, so this kind of summarizes the second part, which came first. Okay, so in this, let me remind you, the second part we try to transfer these the gradient in the w to the gradient in x, meaning that as long as I have a decent bound of the gradient w, I want to say I also have a decent bound of the gradient x. The tool we use is this the key tool is this multiplicative structure. Okay, and we also try to extend it to a neighborhood so that, I mean, later on when we prove the final generalization theorem, we will use it. And finally, I want to remark that even though I showed you most of the analysis in the L2 norm, but everything works into the higher LP norm. Okay. Now let's go to the first part. Okay, why does SGD find this flat local minimum, right? But once I can show that the SGD find the flat minimum, meaning that the W derivative is small, and I can use a multiplicative structure to say that, hey, not only SGD find something which W derivative is small, it also found something that X derivative is small. And X derivative small will finally allow us to prove generalization bound. Okay, so this is the second main piece, and I'm gonna dive into this. Okay, the short answer is that one-line answer, three-word answer is that stability implies flatness. So SGD doesn't always find a flat minimum. I mean, sometimes SGD can just jump here around within different local minimums. For example, this will probably not happen for interpolating solutions. But for non-interpolating solutions, it's almost sure that SGD has a chance to go from one local minimum to another local minimum. But the statement here is a condition on stability. As long as SGD finds the local minimum that is stable in the sense I'm going to define, then this will imply flatness. Okay, so you can think about this as a conditional theorem. Now, what do I mean by stability? Well, stability, I mean, for those of students who have worked on PDEs and ODEs, you know, stability is something that comes a lot, right? It tells you that when your numerical scheme is actually does not blow up. I mean, the short answer is, well, let's compare the stability of gradient descent and the stochastic gradient descent. In fact, they mean a lot of different things, quite different things. So let's just consider the simplest example. Suppose my my function is fx equal to ax squared, and I'm trying to do gradient descent on this function. Well, you know that if you write down this, let's write down what would be the dynamics. Well, gradient f is going to be equals to 2ax. So the gradient descent is going to be x dot is equal to minus 2ax. And you can say that, hey, if I run this gradient descent, and if I want to run this finite step size, if Sn was 1 is minus xn divided by my learning rate eta is equal to minus 2axn. Okay, this is how the ODE integrator works. And this is essentially gradient descent. Now you can ask the question is that for what eta step size is my method gradient descent stable? Well, it's not hard to show that for eta is less than 1 over 2a, and in fact, you're going to monotonally decrease to this solution, which is in this case is x equal to 0. In fact, if x is less than 1 over a, you will still decrease, but you're going to bounce back and forth forward. Okay. But on the other hand, if your learning rate eta or your step size eta is greater than 1 over a, then the problem becomes stiff, and your solution is going to jumping up. So here I'm trying to show that the solution is not going to go down. It's actually going to go up, bounce up and down, not up and down, left and right, all the way to infinity. So this is a stability regime. So therefore, let me write it down. 1 over a is a sharp constant where you can clearly say whether the method is stable or the method is not stable. This is for gradient descent. For stochastic gradient descent, the answer is much more complicated because it's stochastic algorithm. Well, where does a stochastic gradient appear? Well, stochastic gradient descent appear is because my final function that I try to optimize fx is not just one single function. It's actually a sum of a bunch of functions. So in the simplest case, in this illustrative example, it's a sum of two functions, f1x plus f2x. And stochastic gradient allow myself to choose one of these functions, f1 or f2, at every step, and use this gradient to drive my solution to see whether to go to 0 or not. Now, on the left-hand side, I draw a picture where f1 and f2 are very close to each other. They're almost the same. So this inner one, the blue one, is f1, and the second one, outer one, is f2. And in this case, I mean, the same analysis essentially applies. When learning rate is less than alpha 1 over alpha, and then the solution will essentially go down. Okay. But on the other hand, if my f1 and f2 have very different curvature, for example, here f1 is a very sharp, f2 is very flat. And here the stability is essentially going to be dictated by, stability condition is going to be dictated by the curvature of f1, the sharper one. So even you choose eta less than 1 over alpha, because this learning rate is not going to be stable for f1, so therefore you will still experience this blow-up structure, even though this is a acceptable stable learning rate for the overall function. So what this essentially says that a stochastic gradient is going to impose much stronger condition on your learning rate. If your stochastic gradient, if the component functions look very different, so usually the stability requirement for the time step is much more strict. Okay. So let's make it more precise because we want to do some math. Okay. So let's take a look at the stochastic gradient descent, and this is the stochastic gradient descent, right? And what this means is that B is my mini batch size. So therefore, at every step, I'm going to select a batch, and the batch is going to contain some indices, and these will correspond to the samples that I use. And I average that to get my learning gradient, and then multiply my learning rate and up to my solution W. Okay. So as a mathematicians, the first step when you analyze the stability, you always want to take a look at the linear stability, because if you don't have linear stability, everything go out of the window, right? So let's linearize this. We see that the linear stability, which we denote by W tilde, is actually going to given by this formula. Okay. Now, without loss of generality, I can assume my underlying ground truth solution, that the final solution that I converge to, if I converge to be W star to be 0. So therefore, I can write down this very simple formula for my linear dynamics. Okay, it's just a multiply. This is any kind of linear dynamics, right? I mean, if you linearize around your stable solution, then so you will get the linear system. It's just next step is equal to matrix times the previous step. Now, what do we mean by linear stability? So we say that this is a condition that we require our solution to have. Well, we say that the interpolating solution W star is called case order linear stable for this SGD with a certain learning rate eta and with a mini batch size B, if the following thing is true, is that if I take the case order moments of my solution W and then take the expectation. Why do I need to take expectation? Because SGD is stochastic, is random. Okay. So if I take a look at the case order moments of my weights, case order tensor of my weights, it has to be bounded by a certain kind of uniform constant, which can depend on K, but cannot depend on the time step T, C times the moments at initially. Okay. So in fact, this is just really a moment kind of stability condition, right? If you use K equal to 2, this is just a quadratic stability, which people use a lot. But we require a little bit more. We want to say that a case order stable. Okay. So the formula might look a little bit complicated, but essentially just saying that if I measure this stochastic WT, which I get from my SGD, and I want to study the case order moments of it, and I want to make sure that the case order moments does not blow up. Okay. The bigger the K I require appear in this definition, the more strict this condition for SGD, right? Because I mean, low order moments is always easier to guarantee. High order moments are harder because of the polynomial growth. Now let's just write down again this linear dynamics. And in fact, I will call this multiplicative factor after I take the expectation, give it a name, called it T eta B K, where eta is the learning rate, B is the mini batch size, and then K is the moments, degree of the moments I consider. Now, this is just a trivial lemma from any kind of linear stability. Essentially, it says that if you want this thing to stable, what you need is that you need the norm of this operator. This is a huge operator, but nevertheless, we can write it down. You need the norm of this operator to be bounded by 1. Okay, that's all you need. From that, we can try to test this equation with a certain of the, like a certain kind of test functions. The test function we're going to use is just simply, these are the ways which you're not seeing the neural network, but nevertheless, we can use it in analysis once we have the stability condition. We just tested on delta, directed delta vectors. So in some sense, you put a 1 at one single entry of your W, and you do this linear dynamics analysis. And after some, this is a simple, straightforward theorem, maybe not so straightforward, but it's like a one-page proof of the theorem, but I will not dive into the detail. But I will just tell you the result is that if you plug in these test functions and back into this formula and do a little bit of algebra, you will see that as long as this W star is a case order linear stable, and then we get the following result. We have that this flatness, remember this is almost the same as the flatness, right? Except that it's a 2K, but we can define the 2K flatness. This essentially saying that the flatness will be bounded by the following quantity, where W is how many neural network you have, 2B, B is a mini batch size, and eta is a learning rate. So what this says is that you don't need to worry too much about the W because you have this K here. So this 2B and eta are much more important. Now, what this says is that if the neural network is case order stable with a certain learning rate eta and a mini batch size B, and then the W derivative has to be bounded by that. Now, if B is large, meaning that I'm using large batch size, and eta small, meaning that I'm using small learning rate, then this 2B over eta actually could be a fairly large number. And this means that this is the weak bound. This is kind of expected because if I use large batch size and small learning rate, I get more and more close to the gradient dynamics. So therefore, the gradient dynamics it's much easier. If a numerical scheme is close to the gradient dynamics, it's much, much easier for it to be stable, okay? But on the other hand, if you use a small batch size, you use a learning rate, which is not too small, and the right-hand side itself becomes a finite number. And this imposes a very strong condition on your flatness. So the punchline is that if your SGD is case linear stable with a decent, not so small learning rate and a not so large batch size, and then this at your interpolating solution, it has to be, sorry, I'm missing a star here. At your interpolating solution, it has to be flat. Okay, so let me write it down. Large eta plus small b implies flatness, and plus stability implies flatness. All right. So now we're ready to combine part 1 and part 2. Okay, because let me state the following thing. Because this is part 2 and this is part 1. Why? Because from part 1, stability along with eta large, not too small, and beta small, this implies flatness. And then flatness plus this multiplicative structure, multiplicative structure, it implies that I can transfer the W bound on the W derivative to the bound on the X derivative, and the bound in the X derivative, you will see in a second, implies a generalization. Okay. So this now we like stitch everything together. Now, before I show you the generalization results, let me just give you a theorem which combines essentially this part 1 and part 2 together. What it essentially says is the following: is that if you have a neural network, which right, I mean, this is essentially putting these two pieces together, because previously in the part 2 we showed that the X derivative is bounded by this thing you have seen many times, right? W weight divided by X norm. This thing multiplied by the gradient in W. But now in the previous slide, the gradient in W is bounded by this thing, 2b over eta, and this is what we have here. Now we have to change the formula a little bit to match everything together, but that's essentially the idea. Okay. Now, so this is kind of like L2 estimate in a neighborhood of my training point, but in fact, you can also do an L infinity type of estimate, okay? So I'm not gonna list as a separate theorem, but essentially you see that the only difference is that instead of having this W over B here, you have N W over B. But recall that I have this 2K here, 1 over 2K here. So even though the training set might be large, but as long as I can show my neural network, my SGD is 2K stable for some fairly large K, and this take the 1 over 2Kth root power of N is actually going to give me a very small constant. So that's still okay. Okay. All right. Now, here's a punchline. So generalization error. So we're going to use the result we have proved to prove the generalization error. Now everything is going to be fairly easy now because we have done all the hard work. So here, let's set up again. Assume now in order to prove generalization error, we have to show that, I mean, we have the ground truth function, right? And somehow what the function we find, f, is actually going to close to the ground truth function. So let f star to be the ground truth function, which unknown, but somehow generated our training data. And we assume that the training data is generated IID from a certain with respect to a certain measure, and the y is just evaluating this ground truth function at my location xi that I get from this IID sample. And what is the generalization error? Well, generalization error is saying that, hey, let's take a look at let's take a look at the neural network you find and subtract the ground truth. Again, we're going to use a quadratic loss, and then you integrate over all the possible x sampled with respect to the measure mu, and that is your generalization error. Okay. It looks a little bit different from what you see in, maybe a little bit different from what you see in most of the machine learning textbooks, but I mean, essentially it's the same, right? You compare the function you find minus the ground truth function, and you measure with respect to certain laws and integrate over the data. So here you see that I'm integrating over the whole measure of the data, not just the test training points. Now, right, so this is the theorem. The theorem is a little bit long under certain conditions, but let me try to decipher this. So first I need to case order linearly stable. And second, I need these technical conditions which make sure that I can transfer this gradient from my testing date, training point xi to the nearby points, right? This is what I talked about earlier, and this is a very weak condition. And we also need some coverage condition to show that if in fact, so with high probability, any of the x that's sampled with respect to this measure mu cannot be too far away from my training point. The reason is because if you have a sample which is very far away from the training point that you give me, then any kind of like the gradient bound, like what we prove here, any kind of Sobolev bound will not be able to tell you anything about the solution at the training point, which is not close from my test, and like the testing point is not close from my training point. Okay, this is a very reasonable assumption, right? So, and finally, we need some bound on the very reasonable bound on this target function, the true function is that I want it to be bounded, I want the derivative to be bounded. Once we have that, we can prove the following theorem, is that the generalization error is going to be bounded by the sum of these three pieces. So these two small pieces, only the last two pieces are easy because they depend on M1 and M2. So therefore, I mean, as long as my target function is not too weird, it's fine. The first piece is the main thing. It's come from the hard work. What essentially is just copy of the result that I get from the previous slide. And this is that it depends on the ratio of the W1 over my X. So as long as the W1 is small, X is not too small, X is large or of order 1, and this term is bounded. Now you have this term as 2n W over B to the power 1 over 2k, where n and W might be large, but as long as I have a case order stability with k pretty large, right? Like 10 or 20, and this you raise this thing to the power 1 over 2k, and then this is just become a small constant. You don't need to worry about that. And finally, you have this ratio 2b over eta, very important. We need our B batch size not to be too large, right? So that you have some randomness, and also your learning rate not to be too small, right? If your learning rate is small, you go back to GD, so you will not have this generalization. You're stuck at the local minimum. Now the proof is actually very simple. It's just one line. It's just triangle inequality. Okay, here's a proof sketch. So we need to look at this quantity. So we take a look at what if I randomly choose an X, evaluating in my neural network with the parameter case W star, subtract my target function. By triangle inequality, this is equal to this multiply my neural network at a point. So here, let me just draw a picture. So you have this point. Let me just draw a picture. So this is the point X that I want to do this comparison. But with high probability, there will be another point nearby called Xi is my training point, which is going to be within distance eta to it, right? So therefore, I'm going to choose this Xi. But once I choose this I can do triangle inequalities. So this quantity here is going to be equal to neural network difference between X and Xi minus the neural network target difference at the Xi, the training data, minus the target function difference between X and Xi and X. Okay, so essentially, let me just draw a figure. You have two functions. One is F star, the other is Fx and Fw star. Okay, and then you have 2 points. One is X, the other is Xi. I care about the error between these two locations. It's my target function and also my neural network, evaluated X. But I cannot do a direct comparison. So what I do is I do triangle inequality. I go here and go here and go here, okay? Is that clear? But what I claim is that these triangle inequality really help us because the rest is very easy. The first term is bounded. Why the first term is bounded? Because this is something about my F, my neural network. And because I already, this is the difference of my neural network at the two nearby points. But as I said, we already have this gradient of WF bound earlier, we proved. So therefore that term is small. And second, this is what? This is the neural network and the target function at a certain training data. But my function is interpolating. So this is actually exactly equal to 0. And then finally, you have this Xi and an X at my target function. But because of this, my target function is also Lipschitz. So therefore, this is also small. So therefore, we add these three pieces, it's small, okay? Now, this method is useful, right? This method is useful when especially when one thing I swept under the rug is that how do I guarantee that with high probability that any point Xi sample will be close to my training point, right? So this will require some kind of like assumption on your input data distribution, right? For example, if I have some kind of like a uniform Gaussian on the unit sphere high dimension, and unless you have exponential number of points, you will not be able to find another point which close to a point sampling point, right? This is the high dimensional phenomenon. So therefore, in order for this statement to be true, and one have to have some kind of like assumption on these data set. So for example, if the effective dimension of your data set is small, for example, I can have a data set living in high dimensional space, but it's a union of several pieces of low dimensional manifold, and then it works, okay? All right, so previous slide, I show you the generalization, and this slide is trying to see that, this result I get the previous slide, they directly apply to adversarial robustness. Because what essentially, I mean, this is actually a corollary of the previous theorem. So it's essentially what it says is that if you perturb your x a little bit, and then within this delta we get from the previous slide, is that the solution will not change too much. And this is adversarial robustness, right? Because adversarial robustness says that if you change your training point a little bit, you will not get a crazy solution, very different from the solution at your training point. So so we show that if you perturb by a certain distance, delta, at the most delta, you'll get this bound, and it's of order delta. Okay. So summary. So in this talk, I give you one explanation of why does SGD generalize. Is that first step is that if the SGD converges to a solution W star and it's also linearly stable at this W star, then I have a bound on the gradient of F respect to W. Once I have that, I can use a multiplicative structure to transfer this into the gradient in X. Because everything is involved in the gradient, so we call it Sobolev regularization. Once we have that, we can show generalization and also adversarial robustness. Now, there are also several questions that we did not answer. The first is that, what if my W star is not interpolating solution? Then the analysis falling apart. I mean, I don't know how to do that. That's an interesting question. And second is that, what if the loss is not a square loss? Right? I mean, this part we know how to do, because if essentially any kind of smooth loss, I mean, close to the bottom, it actually has to be a quadratic approximation. This is what the physicist tells. Everything is harmonic oscillator. Okay. And finally, what if the optimizer is not SGD, right? I mean, here we proved SGD, but what if we use Adam, we use MS prop, we even use momentum methods? I think the method can be easily generalized to the momentum method, simple momentum methods. But for Adam and MS prop, we don't know how to do that at this point. And we also didn't use all the power of neural network. So for example, we only use the multiplicative structure in the first layer, but multiplicative structure happens in all the layers. I mean, would that help us? We don't know. Okay. Finally, I would like to thank you for giving me this opportunity to share our recent work with you. And I hope it's not too technical, but again, I want to get the main message through is that this level set picture, right? I hope that's intuitive. And if you have any questions, feel free to ask now or email me. And this is our paper, our archive. Thank you very much.